you made it. This is our last video for this particular unit, chapter, whatever you want to call it, partial chapter, I don't know, our last part. And so this is going to focus on stoichiometry and being able to do stoichiometry with solutions, reactions. Really don't overthink this too much. It's actually relatively straightforward. There's lots of crazy variations that we can do if we really want to. And the book shows a method that's related to using the ionic version of it. It's okay. I don't really generally find it necessary most of the time. So I'm going to focus on the more straightforward application of just regularly doing stoichiometry problems with this. So hopefully you'll find this is relatively straightforward and consistent with what you've been doing sort of already. So here we go. Here's the type of question that you'd get with a stoichiometry problem like this. So we'll get how much precipitate would you form? Very common, like a theoretical yield problem in this particular chapter almost always refers to the theoretical yield of the precipitate. So you might have to write and balance your equation first, use your solubility rules, determine what your precipitate is, but it's very common to be a theoretical yield of precipitate, a very, very common style of problem to use. So I'm using the same one that I used in the last video, which is silver nitrate and copper 2 chloride to form copper nitrate and silver chloride. So silver chloride here is our precipitate. So, and this one says, normally, right, what would we do, right? We would do grams to moles, and then moles to moles, and then moles to grams, right? That's typically what we would do if we had, 25 grams of this stuff. We would convert grams to moles, and then we go moles to moles of our product, and then we convert moles to grams. Okay, so very similar to what we're going to do here. The biggest difference now is that we're not given grams, right? We don't have the grams of silver nitrate here. What we're given instead is information about molarity. 18.5 milliliters of 0.250 molar solution. So we have 18.5 ml, and it's 0.250 molar solution. And we're trying to find how much precipitate we can form. So this is what we're trying to find. And that's always going to be in grams. Again, it's a theoretical yield type of a question. So grams is in there. Again, they're giving you, in this case, excess copper chloride. They could give you a limiting reactants problem as well. It's limiting reactants is kind of done the same way here as it was done in the last chapter. So what now, right? Well, normally we would do grams to moles. Well, in this particular case, instead of doing grams to moles, we're going to do molarity to moles. Remember, we've got this equation, molarity equals moles per liter, or we can rearrange it, M times L equals moles. So rather than doing a grams to moles conversion, we simply use the molarity equation to figure out what our moles are. So handy dandy calculator, we would take, clear it out, we would do 18.5, move it over 3 decimal places, 0.185 liters of solution times 0.250 molar solution will give me my moles. 0.0185 times 0.250 gives me a value of 0.004625 is my number of moles. So I'm going to erase this just to give myself some room to go. Oh, sorry. Here, I'll do this. This is the value, 0.004625. That's my calculator value. Again, don't round. We're not using sig figs until the very last step. So make sure to keep some extra digits in there. This really only has 1 extra digit. My numbers in my problem have 3 sig figs. This one right here only has 4. So leave it that way. Don't round it. This is important to remember not to round until your very last step. So 0.004625. All right. That's our value. 0.004625 moles, MOL, of AgNO3. Okay, so there's our wonder fractioning problem. So what would we normally do in our other problems, right? Grams to moles, moles to moles, moles to grams. Same 3 steps, basically. We did molarity to moles. And now we do moles to moles. Remember, moles to moles comes from our balanced chemical equation. So 2 moles of AgNO3 is going to produce 2 moles of AgCl, right? And then our last step is going to be to convert from moles to grams. 1 mole of AgCl is going to be grams of AgCl. And you just use your periodic table to figure out what that would be. So let's see. Silver is 107.87. 868 plus 35.45 for the chlorine gives me a molar mass of 143.32, 143.32. And then it's just calculating like we've normally done. 143.32, multiply across the top, divide by the things on the bottom. So times 0.004625 times 143.32 divided by, well, times 2 divided by 2. So whatever, you don't even have to put that in there. We're done. Again, times 2 divided by 2. They cancel each other out. And our answer here is 0.662855. Again, that's my calculator value. So I got to round it to sig figs, 3 sig figs in my original problem. So I would write this in 3 sig figs. My answer here would be 0.663 grams of AgCl would be my answer to that. Again, it's really not any different than the stoichiometry that we've done. Again, the book teaches an ionic way to interpret it. They say, have you write the net ionic equation first, whatever. Most students by now are more comfortable with writing formula equations, so I say stick with that. It's not going to hurt you as long as you balance your equation, writing and balancing your equation, using it for stoichiometry. It's actually a really good use of a formula equation anyway. Okay, so here's our, I'll show you what this ionic approach looks like so that you can kind of see it. And it works. It's fine. Like I said, it's not my favorite, but I just want to point out that you can do it this way so that you understand how it goes. So this is the what mass of sodium hydroxide. Sodium hydroxide, there you go. What mass of sodium hydroxide needs to be added to 17.6 milliliters of lead 2 nitrate in order to precipitate out all of the toxic lead ions. In other words, here's our PPT right here. So I need to be able to get rid of all of these lead ions. That's what I'm trying to do. So how much of this do I need to add? And I'm looking for grams of this. That's what I'm trying to find. So if we take a look at what this is, the ionic approach simply still has you kind of think about, well, you know, what do I really need in here? Well, if I've got lead nitrate, 7.6 ml, and it's 1.5 molar, I'm still going to do my molarity to moles, and then I'm going to do moles to moles, and then I'm going to do moles to grams. So what does this look like? Okay, moles times, or molarity times liter equals moles. I'm going to be doing this for my lead is what I'm working on, or my lead nitrate. So for my lead nitrate, it is 1.5 molar, right? Times 3 decimal places, 0.0076 liters. 0.0076 liters, again, 3 decimal places. So 1.5 times 0.0076 tells me that I have 0.114 moles of PbNO3 2. That's what that means. Okay, again, I just use molarity. I converted from molarity to moles. So that tells me how many moles of lead nitrate I have. So in terms of my neutralization reaction, sometimes it's easier to kind of see the reaction if you're just looking at the ionic equation. And the net ionic equation for this is lead ions are going to react with hydroxide ions to form lead 2 hydroxide. Okay, pretty straightforward. So let's take a look at this. So how many moles of lead ions do we actually have? Well, if I have 0.0114 moles of lead nitrate, lead 2 nitrate, remember how this dissociates. It's going to dissociate into lead ions and 2 nitrate ions. So if my concentration of lead nitrate is 0.0114 moles, that means I have 0.0114 moles of lead ions that are present. Again, I'm just using that 1-to-1 ratio. So what else do I know now? Okay, well, okay, erase. I'm just going to copy my value down here, 0.0114 moles. Okay, well, how much hydroxide do I need? Well, it reacts in a 1-to-2. So if I've got one of these, 0.0114 moles of lead ion, I'm going to need 1 mole of Pb to 2 moles of OH. Yeah, it's a 2-on-1. I know you can just multiply by 2 times 2, which means, I know what, why am I doing this in the calculator? Equals 0.0228 moles of hydroxide. That's how much of that I need. All right, so now what? Am I done? This is asking me what the mass of sodium hydroxide is that I need. So I've got 0.0228 moles of hydroxide. How do I convert that to mass? Well, it's a simple little stoichiometry thing as well. Oops, I'll get my pen back, sorry. 0.0228 moles of hydroxide OH. When I do this, 1 mole of hydroxide is needed to form 1 mole of sodium hydroxide. 1 mole OH, right? There's 1 hydroxide in 1 sodium hydroxide. And then I can do 1 mole of sodium hydroxide, NaOH, gives you how many grams of sodium hydroxide? In this particular case, it's 22.99 plus 1.01 plus 16 gives me a molar mass of 40.00 grams of sodium hydroxide is equal to 1 mole. I don't know that this really saves you any time. You can tell like I'm not perfectly like stoked about this method. It works. And if you have an ionic equation, I want you to know that you can use that, and you can use your relationship between ions, and it's totally fine. But like I said, I tend to use formula equations and go from there. 0.228 times 1 times 40 divided by 1. So our final answer here is I would need 0.912 grams of sodium hydroxide. Again, it's literally just the same as if we did it with a stoichiometry problem, but I want you to recognize, or at least realize, that you can do it with an ionic equation and not worry if you're missing some pieces. So don't stress about that. All right, last one, I believe. There we go. Limiting reactants problem is our last one for this part of the unit. So how do we deal with limiting reactant problems? And again, this is an example. What I would strongly recommend that you do right now is that you hit pause, right? Hit pause on the screen, write it down, and see if you can work it out, because doing limiting reactants with solutions is exactly the same as doing limiting reactants with solids, right? You do your 2 Stoich problems, you figure out which one is your smaller answer, basically, and that's your value that you can use. So again, it's still the same kind of idea, figuring out what your limiting and excess reactants are. So like I said, I would hit pause if I were you. I've given you the equation. I believe it's balanced. Yeah, it looks balanced. So hit pause and see if you can figure out how you would attack this. I always start by labeling my equation. I've got 125 mils of 0.2 molar sodium chromate, and I have 75 mils of 0.4 molar nickel 2 sulfate. Okay, which one? Yeah, how much precipitate will form? And then you can see the second question, will the resulting solution be green or clear? What? By the way, this is the piece of information that you need. Green, nickel is green as an ion, nickel 2+. Kind of like copper 2+ is always blue. Nickel is a really poisonous looking green color. It's lovely. Anyway, just so you know, that's how you answer that part when you get there. So I'm going to use my molarity equations. Molarity times liter equals moles. I'm going to do the same thing here. Molarity times liters equals moles. I'm just going to do it twice. So 0.125 times 0.2. And this is going to be 0.075 times 0.4. And those will give me the moles of my 2 reactants. 0.125 times 0.2 gives me a value of 0.025. And then 0.075 times 0.4 gives me a value of 0.03. Okay, so again, I'm going to label this up here so I can erase it and give myself some room. 0.025 moles, and this is 0.03 moles. So there we go. So remember that when you are doing limiting reactants problems, you can't always just jump to a conclusion and say, well, that one's less, so it's got to be the limiting reactant. You have to take into account your mole to mole ratio and make sure that you know what it is. In this case, it's pretty easy because my mole to mole ratio is 1 to 1 to 1. So I'm going to show it the long way just to kind of remind you that you need to make sure that you take that mole to mole ratio into account. You also need to know which one your precipitate is. It doesn't say. So you got to use your solubility rules. I know from NaCl that sodium compounds are never our precipitates, so this one's got to be aqueous. If we have a precipitate, it's going to be this one, so this is going to be our solid. So this is actually the stuff that we're looking for. That's the goal that we're trying to get to. So here's how I would do this again. I'm going to do it the long way, even though you may think that you can kind of jump to a conclusion. Again, you're setting up a mathematical argument. You need to prove it. Don't just jump to a conclusion. So this is 0.025 moles of Na2CrO4. I know that these are in a 1 to 1 ratio. 1 mole is going to make 1 mole of NiCrO4, nickel chromate, nickel 2 chromate, Na2CrO4. And then I'm going to do my last part is I'm going to convert it to grams. I might as well just do it now because I'm going to use it for both and see what we get going on there. So my molar mass of nickel 2 chromate. Nickel is 58.69. Chromium has a molar mass of 51.996, so basically 52.00, plus 4 oxygens, 4 times 16, gives me a molar mass of 174.69 grams of NiCrO4. Okay, 1 mole. Okay, there we go. I'm going to do the same thing for my other one. Again, I know I'm doing this a long way. Again, I'm setting up that mathematical argument. I'm showing my work. It's fine. I know it feels a little tedious, but you'll need to be able to do this with certain problems anyway. So like I said, I'm just going to set it up and show it. Nickel sulfate, 0.3 moles of nickel sulfate. 1 mole of nickel sulfate can produce 1 mole of nickel chromate, NiCrO4, and yeah, it's nickel 2 chromate the whole time. 1 mole of this stuff weighs 174.69 grams. And again, it's the same compound, nickel chromate, RO4, sorry. All right, now I'll do my calculations and see which one we got. So 0.025 times 1 times 174.69 would give me a mass of 4. Well, we've got 3 sig figs. Oh, let's do 3. Okay, let's do 2 sig figs. I don't like doing 1 sig fig. So we'll do 4.4 grams according to this one. And the bottom one, 0.03 times 174.69 gives me a mass of 5.2407, so 5.2 grams. Again, I know that in this particular one that I have on the screen here, that because it's a 1-to-1, you can kind of see which one's the limiting and the excess reactant. This one has less because it's in a mole-to-mole ratio. I know. I'm just working it out like you would for normal problems where it's a little bit longer. Okay, got my 2 answers. Which one's my theoretical yield? My smaller answer right here is always a theoretical yield. That's my theoretical yield right there. So that means this is my limiting reactant, and that means this is my excess reactant. Okay, the theoretical yield, whatever this is, nickel NiCrO4, and that means that the Na2CrO4 is the limiting reactant. So now I know how much precipitate will be created. 4.4 grams of precipitate will be created from this. Now the last question is a little bit trickier. Will the resulting solution be green or clear? Okay, and that's a tricky one. So let's stop and think about this for a second. What does this mean in terms of what's happening in our product? I think I have this on the next page. Hold on. There we go. So this is our LR, and this is our EX right here. Okay, and this is our PPT. Again, I'm just focusing on the second question. So let's think about what's happening here. Limiting reactant, excess reactant. This one was 0.025 moles. This one was 0.03 moles, right? Okay, so will the solution be green or clear? So this is our limiting reactant. So let's think about what's happening here. I have 0.025 moles of this. I have 0.025 moles of this. I started with 0.03 moles of this and 0.03 moles of this. So what did I make? What did I make here? Okay, I made this stuff, right? Nickel chromate. How much of that did I make? What's my limiting reactant? Okay, so this stuff is my limiting reactant, and it's in a 1-to-1 ratio. So that means for my product, if I started with 0.025 moles of a limiting reactant, and it's a 1-to-1 ratio, I only made 0.025 moles of this stuff. That's all I made. Again, all of my limiting reactant got used up. So what does this mean? This is a limiting reactant. The sodium is a limiting reactant. All of this and all of this got, well, I don't want to say got used up, but are the limiting reactants, are the ones that I got to take a look at. Well, where did these end up? The chromium, the chromate, all of it ended up right here. All of it, right? All 0.025 moles of that stuff went from being in an ion form to being bound up here in this stuff. Now, what happened to our sodium? Okay, this is where the ionic equation piece actually kind of does help, right? I started with sodium ions. None of my sodium ions actually got used. They're still there. 0.025 moles. And they are still running around as sodium ions, swimming in the pool. All of the chromate got used up and is bound up now in the precipitate. 0.025 moles of precipitate got used. So let's take a look at our nickel. This is actually the hard one. I'm going to do the easier one first. So let's look at the sulfate. Okay, the sulfate. How much of that got used? Well, none of it, right? Sulfate is a spectator ion. None of it got used. So this 0.03, where is it now? Well, it's all right here, 0.03 moles. Still left over. Okay, again, none of it reacted. It's a spectator ion. The nickel is now the tricky one. And so this is the one that we'll take a look at right now. Okay, this is the tricky one. Okay, the nickel got bound up into our precipitate as well. But take a look at the amounts. Take a look at the amounts. We only made 0.025 moles of nickel chromate. We only used 0.025 moles of nickel. We started with 0.03 moles. 0.03 minus 0.025 is a leftover amount. And again, I know this is what you guys would do. That means that there's 0.005 moles of nickel, Ni2+, in excess. Left over. It's still there. It's still present, okay? Most of it gets bound up in here, but there's still just a little bit of it left over. Again, we didn't use it all. And this is where the ionic equation part becomes really important. So what does that mean? Is our resulting solution green or clear? All right, well, think about what we've got in our product. Here is actually what's present in our final container. We've got nickel chromate, nickel II chromate at the bottom. We've got sodium ions dissolved in solution. They are clear. We've got sulfate ions dissolved in solution. They are clear. And we have a little bit of leftover nickel ions up above. They are not clear. They are actually green. So this solution, this isn't a whole lot. This solution, the remainder of it would still be just a little bit green because that nickel is in excess. It's not all bound up and there's a little bit of it left over. This would be a toxic solution that's left over. The chromate getting takeout's good, but the nickel ions would still be present in excess just a little bit. So our remaining solution would be a little bit clear. So this is how we can use ionic equations with limiting reactants problems to take a look at amounts in excess and to give us some information about those resulting solutions, remembering that there are still some pieces, our excess reactants are still present in that container. They don't leave. Okay, so there you go. That was kind of a tough part. This last part right here is a little bit harder. Most of them are really just doing the predicting the amount of products, but that's how you figure out some things about amount and excess and being able to make some conclusions about your resulting solution. So there you go. I hope you liked it. That was the last one. Have a great weekend, and I guess I'll see you after the homework. All right, have a good one, you guys. Bye.